We're used to solving algebraic equations, right? Or logarithmic equations or exponential equations. So for example, we're used to solving something like e to the x is equal to 5, okay? And we learned last year that, with each type of equation, we have different tools that we go to in order to solve them. Like, for example, when I have an exponential equation, I take the ln of both sides, right, in order to isolate x, okay? In this section, we're going to be talking about trigonometric equations. And again, the purpose, when we need to solve an equation, the purpose is always to isolate x, all right? So suppose the equation that we're going to solve is a very basic trigonometric equation. Cosine of x equals to a half, okay? We want to solve for x. We want to isolate x and solve for x. So basically, what do we do when we solve an equation? We want to find all of the values of x that would make this equation true, okay? So let's take a look at x. What we want to find are all of the values so that when we put them into this equation, cosine of those values would give us a half, all right? So if we just think in the first quadrant, okay, just in the first quadrant, if I asked you for what angle is cosine equal to a half, what would come to you? What angle? 60 degrees or pi over 3, right? This is why you need to know those like this. So that's just in the first quadrant, okay? Now you know that in the fourth quadrant, there's a corresponding angle where cosine is also a half, right? What's the pi over 3 the angle that corresponds to pi over 3 in the fourth quadrant? How much pi over 3? Negative pi over 3, or if we're going 5 pi over 7 pi over 3, okay? 5 pi over 3. So now, take a look at the graph of cosine of x, all right? What we want is we want to find all of the x values for which cosine has a y value of 1/2. This is y equals 1/2 right here. All right? So if we draw that dashed line at y equals 1/2, look at how many points there are in that section where the x value would make cosine equal to 1/2. Okay? So I have this point here where cosine is 1/2. I have this point here where cosine is 1/2. Another one where cosine is 1/2. Another one where cosine is 1/2. Now, let's examine these a little bit more closely. So take a look at that first point where we said x is equal to pi over 3. Well, if I take that point, and from that point, if I go a distance of 2 pi, now I have pi over 3 plus 2 pi, and cosine is equal to 1/2 again. If I go 2 pi again, I'll have another point. If I go 2 pi in this direction, I'll have another point. So another way to write that is pi over 3 plus a series of 2 pi's. So plus n times 2 pi, right? So if I go from pi over 3 over 2 pi, and then twice 2 pi, and then 3 times 2 pi, and then 4 times 2 pi, or negative 1 times 2 pi, negative 2 times 2 pi, then I hit all of those points. Now, another area where that happens is 5 pi over 3, right? And from 5 pi over 3, if I go 2 pi, I have another one. If I go 2 pi this way, I have another one. So it's 5 pi over 3 plus another n times 2 pi, and we write it cleaner as, 2n pi. All right? So what did we do? Let's just recap. We were tasked with for what values of x is cosine equal to 1/2. And we figured out that on the unit circle from 0 to 2 pi, that happens at pi over 3 and 5 pi over 3. But if we expand that over all reals, then we know that that happens at pi over 3 plus 2n pi, 5 pi over 3 plus 2n pi. All right? So now, the questions that you're going to be asked are you're going to be asked them in two ways. One, it'll say solve the following equations. And when it says solve the equation, you assume that it's over the entire domain of all reals. And then you have to add your 2n pi's or your n pi's. Sometimes, though, it gives you a restricted domain, okay? And it just says over, the domain 0 to 2 pi, in which case we just have to give the two answers, pi over 3 and 5 pi over 3.
Do you add
Wait, yeah.
Do you add the specific domain for each one, like cotangent incident to them?
Right.
You would do the one that matches cotangent,
right.
Or always do okay.
Yeah.
So you add this. Why is it negative?
Because when we do 2n pi, n can be either a positive or a negative number, right? So if n is positive, we go 2 pi to the right. If n is negative 1, we go 2 pi to the left.
And then the sign would just be whatever's in the first two quadrants?
Yes, correct. Right. It's the two that make the true, right? Because if it was negative, then you would take the two values in the two quadrants that make the sign negative. Okay? All right, let's do this one. So to solve these, we're going to use algebraic techniques. Oops. That involves factoring and like everything else, combining like terms, squaring, all of that stuff. All right, so look at this one. I have 4 sine x equals to 2 sine x plus root 2. So immediately I think, okay, what if I subtract 2 sine x from both sides? The trick is you have to isolate x, right? So this will give me 2 sine x is equal to root 2. Now, I can divide both sides by 2 to get sine x on its own. So sine x is equal to root 2 over 2. All right? And then I think to myself, okay, for what angles over the interval 0 to 2 pi, pi over 4 and 3 pi over 4. So x is pi over 4 and x is 3 pi over 4. Now, because it says solve the equations without a limited domain, we assume it's over the domain of all real numbers. So we're going to say plus 2n pi plus 2n pi. All right? So that entire thing is the solution. All right. Let's take a look at this one. Here we have 3 cotangent squared x. So what are we going to do immediately? Subtract the 4. So 3 cotangent squared x is equal to 3. Cotangent squared x is equal to 1. So cotangent of x is equal to what? Square, which is plus or minus 1. So that means now I want to solve for all the values where cotangent of x is 1 and negative 1. So these are our pi over 4s. So it's 1 at pi over 4 and where else? Not 3 pi over 4, but 5 pi over 4. Right? That's in quadrant 1 and 3. And then where is it negative 1? 3 pi over 4 and 7 pi over 4. Okay. But now, okay, so now let's just take a look here. So this is pi over 4, and then 5 pi over 4. And I have, what is this one? 3 pi over 4 and 7 pi over 4. Okay, so take a look at the pi over 4. Where is the next one after I go how many degrees? pi, right? And then the next one is after I go pi. So it's just pi over 4 plus n pi. So this can be summed up, the purple ones can be summed up as pi over 4 plus n pi. What about the blue ones? 3 pi over 4 plus n pi. All right? Yeah.
Couldn't you just do pi over 4 plus n pi over 2?
You can do, okay, so that's what I was going to say next. And then if you realize that, look, from pi over 4 to 3 pi over 4, it's 90 degrees, right? And then it's 90 degrees, and then it's 90 degrees, and then it's 90 degrees. So you could also do pi over 4 plus pi over 2n, right, n pi over 2. Okay? And that'll sum up everything. So either or is fine. Okay? Because from here, I go pi to the other purple one, and then pi to the other purple one. But my solutions are the purples and the blues. So from here, I can go pi over 2, pi over 2, pi over 2, pi over 2. Remember, this is 45 degrees. This is 135. That's 90 degrees, and then 90 degrees, and then 90 degrees, and then 90 degrees.
This is just a notation question. When we have more than one solution, do you want a comma or two separate x equals x equals?
Two separate x equals. Yeah.
Why didn't you include 5 pi as a whole and 7 pi as a whole solution?
Because I could, if I had done like pi over 4 plus 2n pi, and then it would have been 5 pi over 4 plus 2n pi, but then I found a shortcut which said, okay, from here, if I only go 1 pi, I go to 5 pi over 4. If I go another pi, I get back pi, 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 right? So by doing that, I'm able to cover all of them. Okay? All right. Here's another one. What do you guys think? Let's bring, okay, so somebody would, I'm sure there is at least one person who would say, okay, let's just divide everything by sine x. Okay, I guess mathematically there is nothing against, I mean, you could do that, okay? However, when you do that, you're getting rid of that sign and you're eliminating part of the problem which would have given you further solutions. So why don't we try to keep the sign there, but think of another way? Why don't we move this to this side, set it equal to 0. Now what can we do? Factor. I can factor out a sine x, and I get 2 cosine x minus root 3. This is what I love about these problems is no two are the same, right? So you really have to think about these. You can't just go on autopilot and run through these. You really have to be actively engaged in what you're doing. Now, I'm practically done. We've learned in Algebra 2 that if you have two things that multiply to 0, you can set each one of them equal to 0 separately. So now I can say sine of x is equal to 0. And I can say 2 cosine x minus root 3 is equal to 0. And all of a sudden, I have 2 mini problems that I'm solving. So now, where is sine of x equal to 0? 0 and 2 pi. 0, pi, and 2 pi. Now, let's take a look at our domain. Take a look at what this says. This says find the solution of the equations over the interval 0 to 2 pi. That means we're not going to keep going plus n pi plus n pi. It's just from 0 to 2 pi. Now, these brackets and parentheses means include the 0. Don't include the 2 pi. So exclude 2 pi. Is that what Alex says? Alex is right. Okay? So sine of x is 0 at 0. Pi. Yes, it's 0 at 2 pi, but it's not asking us to include that, so we're good with 0 and pi. All right? In the other one, 2 cosine x is equal to root 3, and cosine of x is equal to root 3 over 2. So tell me, where is cosine of x equal to root 3 over 2? At the pi over 6's and 11 pi over 6. So finally, x is 0, pi over 6. We can just list them here. 0, pi over 6, pi, 11 pi over 6. It's good form to list them all from, in increasing order. If it's without the n pi's, just go ahead and list them. But if you've got the plus 2 n pi's, separate them so visually we know what we're talking about. Huh? 11 pi over 6.
How do you know not to include the n?
Because in our directions it says just over the interval 0 to 2 pi. So just in that one period.
So here was like all real.
Here it was always, because it didn't specify, it says solve, so find all solutions of x. Okay. All right. So here, so subtracting the root 2.
Take out a 2.
No, because there's 1 percent. Take out 2.
Okay. What do you guys think? Take the what? Can we factor a cosine out from everything though? No. Because there's a root 2. So now what? So we're going to split it down the middle and we're going to factor by grouping. From the left-hand side, we can factor out a 2 cosine x, and that gives us a cosine x plus 1. Yes? 2 cosine x plus 1. Minus, we'll factor out a root 2, and we get 2 cosine x plus 1.
Wouldn't it be minus 1?
Well, I factor out a minus root 2.
So then wouldn't it be plus root 2?
If you factor out a minus, that means this changes sign and that changes sign. Because let's work back. If we distributed this back, it'll be negative, negative. Okay? All right. So now I have 2 common terms, which will factor out. And that will leave us 2 cosine x minus root 2 equal to 0. And again, this is called the zero product property. If 2 things multiply to 0, then they can each be said equal to 0 independently. So in the first case, 2 cosine x plus 1 is equal to 0. So cosine x is equal to negative a half. 2 cosine x minus root 2 is equal to 0. So cosine x is root 2 over 2. All right. So where is cosine equal to negative a half? Pi over 3 and? Okay, so it's the...
Oh, that c is down there, so it's not that.
So 2 pi over 3 and 4 pi over 3.
What about negative pi over 3?
But remember, it was within a domain of 0 to 2 pi?
And to be positive, it was negative pi over 3 because
Huh?
even if it was, no.
Right. So, right. So you have to make sure that we're in quadrants 2 and 3 and within 0 to 2 pi. Okay, so where is it root 2 over 2? These are the pi over 4s. So it'll be pi over 4 and? What do you think? 7 pi over 4? In quadrants 1 and 4. 1 and 4. So now, this will be pi over 4, 2 pi over 3, 4 pi over 3, 7 pi over 4. Okay? All right. So these are the basic ones where you could just use your algebraic methods. Most of the time, you're going to be using trig identities in conjunction with algebraic methods. So Let's use some trig identities along with our algebraic methods to solve these. Again, we're solving over 0 to 2 pi. Yes?
You said 6 pi over 3 for the one above?
No. 4 pi over 3 and 7 pi over 4.
Oh.
Yeah. Okay. So, all right. So take a look at this one. It says find all solutions over 0 to 2 pi. Now, what we have here is a cosine and a sine. We don't want that. What we want to do is make it a homogeneous problem where we have either all sines or all cosines. Okay? So, we then have to look for an identity that relates a sine to a cosine. Now, here's a little trick. If you have a function squared, then immediately you go to which of your identities? The Pythagorean identities. So here I have sine squared x. And remember, sine squared x plus cosine squared x is equal to 1. Remember also that you can rearrange these as you wish. So sine squared x is equal to 1 minus cosine squared x, right? So what if I take this and I substitute for sine squared x? So leaving everything else the same, 1 minus cosine x is equal to 2 times sine squared x. But what is sine squared x? It's 1 minus cosine squared x. Now this is easier to work with because I only have cosines, not cosine and sine in the same equation. Okay? So let's distribute the 2 and we'll get 2 minus 2 cosine squared x. Now, when in doubt, bring everything to the same side and let's see if we can solve. So this will be 2 cosine squared x minus cosine x minus 1 is equal to 0. Is that right? Okay, I brought the 2 over here. It became minus 2 plus 1 is minus 1. Okay, now I'm going to factor. Okay? Do you remember how we factored 2x squared minus x minus 1? Right? That would have been 2x and x. Now we're going to get 2 cosine x cosine x. Okay? We need two numbers that are going to multiply to minus 1. So obviously that's a 1. So I do the guess and check. And here's how I do it. If I multiply these two, it's going to be 2 cosine x. If I multiply these two, it's going to be 1 cosine x. Now, I need to be left with a negative cosine x. That means the bigger ones must be negative, right? So this should be negative so that I get negative 2 cosine x. And that's a positive, so I get 1 cosine x. Okay, now...
Yeah, don't 2 cosine x positive?
Right, but if you do, the multiplying, 2 cosine x times minus 1, the outer terms, that'll give you negative 2 cosine x. Remember, how do we first, outer, inner, last? Right? You multiply the first terms and you get 2 cosine squared x. The outer terms will now give you negative 2 cosine x.
Yeah.
Okay? I'm going to try from now on to not use the term FOIL because it's not mathematically as accurate. This was a thing that people came up with to make math more accessible to people. I want to use as much as I can the technical terms. So instead of FOIL, that's really called distributive property, right? We're distributing. All right. So now I'm going to set each of those equal to 0 and solve. So 2 cosine x plus 1 equal to 0. Cosine x minus 1 equal to 0. Cosine x is equal to negative a half. Cosine x is equal to 1. So where is cosine x equal to negative a half? In the second quadrant, 2 pi over 3. And the next one over 4 pi over 3. Here, where is it equal to 1? This is the x value. Where is it equal to 1? At 0 and pi. Pi is negative 1, sorry, so it's just at 0. So, in all, x is 0, 2 pi over 3, 4 pi over 3. All right, so let's move on to this next one. Same situation. Okay. Let's factor out a cosecant squared x. We're going to factor by grouping. And we're going to get cotangent squared x plus 2 minus, I'm just going to factor out the minus there. And I'm going to get positive cotangent squared x plus 2. Okay. So I have cosecant squared x minus 1, cotangent squared x plus 2 equal to 0. Okay. So for that first one, you can say that this is equal to cotangent squared, and you could just set that equal to 0, or you could just leave it the way it is, and you could say cosecant squared x is equal to 0. Is equal to 1. So cosecant of x is equal to plus or minus 1. Here, cotangent squared x is equal to negative 2. And does that work?
No.
No. So from there we get no solution. But you can get no solution. How about cosecant of x is equal to 1? Where is cosecant equal to 1? Cosecant is the reciprocal of the sine, remember? So at pi over 2. And where is it equal to negative 1? 3 pi over 2. Because it says cotangent squared is equal to a negative number. You can't square and have a negative number. All right. Huh? No i's in trig. No i's in trig. That we know that tangent squared x plus 1 is equal to secant squared x. Yes? Now, that's fine, but here I just have tangent and secant, not the squared. In order to make them into squares, I need to square both sides. Square this side, square this side. So on the left-hand side, I get secant squared x plus, don't forget the middle term, 2 secant of x plus 1 equal to tangent squared x. Okay? All right, so now what is tangent squared x equal to? Secant squared x minus 1. So let's just copy down what we have here. Equals tangent squared x is secant squared x minus 1. And now look at what happened. What happens to the secants? They can cancel and go away. When you have identical terms on either side of the equal sign, you just get rid of them. So now I just have 2 secant of x equal to negative 2. Secant of x is equal to negative 1. Because of this identity, tangent squared x plus 1, I move the 1 over. So now, where is secant, which is the opposite, the reciprocal of the cosine, equal to negative 1? Cosine at pi. Just pi. Okay? All right. Yeah. Okay, the next one is very, very similar. So I'm going to give you 2 minutes to work through the next one on your own. I'll stop this for 2 minutes. All right, so here we have, when we square both sides, we're going to get cosine squared x is equal to sine squared x minus 2 sine x plus 1. Cosine squared x is what? 1 minus sine squared x. Now this time the sine squares don't cancel, but the ones will. So I'll get 0 is equal to 2 sine squared x minus 2 sine x. Okay?
I subtracted,
So now can I get rid of all of the 2's here? Right? I can get rid of the 2's because I could just divide out of 2. So I have sine x times sine x minus 1 equal to 0. So I get sine of x is equal to 0. Sine x minus 1 is equal to 0. Well, I factored out a sine x. I factored out a sine x from here. Huh?
the way I did it is, instead of changing the cosine squared x,
Where is sine of x equal to 0? At 0 and pi. Where is sine of x equal to 1? Just pi over 2. Now, how did we come up with all of this to begin with? We came up with it by squaring both sides. When you square both sides, you artificially introduce solutions to a problem that would otherwise not have been there. You introduce extraneous solutions. I wasn't too worried about it before when we got pi, but when you get multiple answers, please check your answers. So let's check. So the first one, when x is equal to 0, does that work? Is cosine of 0 equal to sine of 0 minus 1? What's cosine of 0? Really? Cosine of 0 is 1. Is that equal to negative 1? No. So that doesn't work. So number 2, x is pi. Is cosine of pi equal to sine of pi minus 1? Cosine of pi is? That one works. And what about pi over 2? Is cosine of pi over 2 equal to sine of pi over 2 minus 1? What's cosine of pi over 2? 0? Right. So the answer is just pi over 2 and pi. Now, I didn't get a chance to do the last one. I'll just pick up from it tomorrow, next time. So I think there's just one of those in the problem set that you can skip. Well, next time. You can do the entirety of the homework except for the last problem. Okay? And if you want to go ahead and try the last problem, please feel free. Next class.